Hi, Richard here from Past That Science. A topic that we're looking at today is three-phase. You are very likely to get some questions come up about three-phase, and I'm going to be going through today a couple of questions that you might get that are going to be fairly easy wins. They're going to be fairly straightforward. One of the questions will be about waveform diagrams. The other question about the advantages of three-phase systems, and I'm not just going to go through them. I'm going to try and explain some of those as well. First of all, on the screen you see on the left there, that is what they call a waveform diagram. There's lots of information there that's missing, but that's the waveform, and that's kind of looking at what an AC waveform will look like. And it may be that you may be asked to draw one of those or something similar to it. So that's a single waveform. You may be asked to draw a three-phase waveform, and I'll show you how to do that. The characteristics of a three-phase system, as I'm sure your tutor has explained, it's a system that's got three line conductors, the phases of which are displaced by 120 degrees, and I'll kind of show you what that will look like on a single diagram in a minute. But anyway, the drawing that you're going to produce is going to need to show the waveforms for each of those three phases or three line conductors, and I'm going to show you how to do that and map that correctly with all the correct detail. So this may be the sort of question that you may be faced with. Draw a diagram to show the waveforms of a three-phase supply with the correct phase displacement over one 50 Hz cycle. So a lot of information to get in there, I think. But if it was me, this is how I'd go about drawing this diagram. So first of all, I need to draw myself a couple of axes. So I'll draw a vertical line and a horizontal line. And I would mark then the vertical line with a plus and a minus to show that the waveform can go above 0 and below 0. And I'm also going to put another, so you can see the dotted line there. Because what I'm going to be doing is making a set period of time. Don't forget this axis here, this axis, your horizontal axis, that is time. And I need to demonstrate my understanding of what one 50 Hz cycle looks like. So a little bit of maths involved. What they're talking about here, one cycle is one period, as they call it now, or periodic time. So that's what I'm going to be fitting into this gap here. It's one time period. Now the time period can be found by using this formula. P is 1 over F, where P is the time period in seconds, F is the frequency in hertz. And so your frequency is 50 Hertz. So if I was to find 1 over 50, I would get 0.02 seconds or 20 milliseconds. So what I'm going to be cramming into the gap, that's this gap here between there and there, that's going to be 0.02 seconds. So if it were me, I would be labeling that with 20 milliseconds, 0.02 seconds. What I then might do, the fact I've got to cram 3 of those waveforms over the 3 in the space given there, is that I'll divide maybe that horizontal line into 3 and give myself 3 little marks. Now the reason why I would do that is because those marks will show where those phases will start to rise from the 0 point. So the first one would rise from this point, the second one would rise from this point, third one would rise from this point. Bear in mind, you've got to draw everything coming backwards this way. But let's put the first waveform in, and I've done this on PowerPoint because it's easier to do that than on a trackpad. But there's your first waveform, and I'm going to label that as L1 because that's the wave that's in the first line conductor. This one then will be line 2, and you can see that the start of the positive voltage is starting at the second dot that I drew, and that is L2, and then here comes the third one, giving us that correct displacement. Label that as L3. Now, so what are we looking at here? These are your 3 line phases, which you may want to do yourself a favour by then adding another label saying and demonstrating, showing that they are 120 degrees apart. So what have we shown here with the drawing? It's a waveform diagram that shows the three-phase supply having 120 degree phase displacement over 150 Hertz cycle. So that's where the 20 milliseconds comes from. So if you were to produce that drawing, in answer to that question, that would be a full 3 points. There's another question you might be faced with, something to do with the advantages of balancing the loads on a three-phase 4-wire system. So what we're talking about here is a variety of single-phase loads, lighting circuits, power circuits, heaters, cookers, whatever. Across a three-phase 4-wire system, there are some distinct advantages. I'm going to list 2 of them for you immediately, and they are that by balancing them as closely as you can, so that the line currents are fairly similar in each of those line conductors, you can have smaller system conductors, and it will also allow you to have lower current rated switchgear. And I'm going to try and show you how that happens in case you've got any kind of doubt. I want you to imagine then that I've got 9 10 amp single phase loads, and I've got for the minute just a single phase supply, and I'm going to connect all of those loads to one single phase supply. Now, as you can imagine then, the current being taken by the line conductor then is going to be the sum of all of these. So as I've got 9 10 amp loads, then it doesn't take a mathematician to work out the total load on that conductor would be about 90 amps. So if you think for a minute about the size of cable that is actually going to need, what size cable is going to take 90 amps? Probably something like 25 mil, depending on what the cable is and what the installation conditions are, but I would guess something around 25 mil for that. Quite a big conductor. And because the load is 90 amps, you're certainly going to need 100 amp switchgear. Now let's compare that to a three-phase system. So that's taken care of 2 of those advantages. There's another advantage in as much as that you can reduce inconvenience in the event of a fault. And by that, what I mean by that is if you have a fault on one of the line conductors, it could be that the other 2 keep going. If it's got a 3-phase circuit breaker on the end of it, then that's not going to kind of happen. But if it's an old system with fuses, then you could still get the other 2 keep going. And what I mean by that is there's my 9 single phase loads. I've got them spread across the 3 line conductors. And what if I had a fault on one of those conductors and the protective device was going to operate, it means that these two, lines 2 and 3, would indeed carry on working. So it'll minimize the inconvenience a little bit. So hopefully that's taking care of that reason. And there is another one, which is that you get reduced neutral current with a balanced three-phase system. And in fact, if you have a single item, a single three-phase piece of equipment, such as a motor or a three-phase heater, they may not need a neutral conductor at all. And I'll show you how that works. So this is a phasor diagram. It's a representation of the three-phase load that we were looking at earlier, where we have then your first line conductor is carrying 30 amps. And then, as you know, the phase displacement for each of the line conductors is 120 degrees. And then, so there's your second line conductor, and then another 120 degrees is your third line conductor. Okay. Now, the neutral current is described as the phasor sum of the currents in the line conductors. Basically, what it means is we're going to add these phasors all together. So let's do that then. So if I was to take line 2 and add it onto line 1, we would do something like this. Just imagine that then. So what I've done, I've taken the current in this line conductor with its magnitude and its direction and added it onto the end of line 1. I'm now going to do that to the same, take line 3 and I'm going to add it onto line 2. So let's do that. So I've done that with the same direction and magnitude, and you can see that the arrow has taken us straight back to this point here, which is 0. That's the 0 point right in the middle. So with a balanced three-phase load, the neutral current will be 0. And like I said, for single items of three-phase equipment like motors or heaters, they may not require a neutral conductor. If it's a motor, it's very uncommon to see a neutral conductor on a motor. Please do not do that though if you have an unbalanced load. Please do not omit the neutral conductor. You definitely need the neutral in there if you're trying to do lots of single phase loads, right? Don't omit the neutral. Just to recap then, what we've done today is looked at drawing a waveform diagram for a three-phase supply with the correct phase displacement over one cycle, one period of a 50 Hertz supply. And then we just spoke about some advantages of three-phase balanced systems. Those two answers there are worth 3 points each. Okay. Good luck and pass that exam.